Okay, welcome back. We are continuing the example we were working on in the previous video. We had come up with a formula that looks like this for the population of a city that we were looking at T years after our starting point, which was the year 2000. Now we're going to answer the question, in what year was the population 20,000? If this formula applies, and if it did apply in the past, then that means that sometime in the past, the population was even smaller than 25,000. So when, according to this model, would that have happened? What year would give us a value for this population function that comes out to be 20,000? So we're taking this formula, we're setting it equal to 20,000 for the population, and we are solving for t. So set up the equation like this, and to solve for t, the first step would be to divide both sides by this number in front of the e. Divide both sides by 25,000. So then we get e to the 0.018 and so on times t equals 20,000 divided by 25,000 comes out to be 0.8. How do we get the e out of the way? We've done that often enough that by now you should know we undo the e with the ln, the natural logarithm function. So take ln of both sides and we get this number times t equals the natural logarithm of 0.8. And when we have a number times t, and we want just plain old t by itself, divide both sides by this number. So t is the natural log of 0.8 divided by this number. On the calculator, that looks like the ln of 0.8 divided by, and remember I had that number stored in the calculator's memory as b. So I just pushed alpha and then the button with the b above it, and the ln of 0.8 divided by b is negative 12.2 something, about negative 12. So if t equals 0 corresponds to the year 2000, then when t is negative 12, that's 12 years before that starting point. In the year 2000 minus 12, which takes us back to 1988. So if this formula still applies back before the year 2000, it predicts that we would be talking about the year 1988, giving us a population of 20,000 people. Okay, next example. Now we're getting into exponential decay, where something gets smaller over time. So suppose a substance decays exponentially. That is, the amount after t years follows a model that looks like this. A of t equals some number that I'm calling a sub 0. So that's the initial amount, times e to the some other number, which I'm calling k, times the variable t. So instead of just using a and b, I'm using a sub 0 for the initial amount, and k for the number up here times t, which the function depends on. And the k is a negative number if we're talking about exponential decay, something that gets smaller and smaller over time. There is initially 800 grams of the substance. After 5 years, there is 400 grams. So that's telling you that after 5 years, when t is 5, the amount a of 5 should be equal to 400. And then the question is, at what time will there be 100 grams? Okay, so here's our formula. A of t equals a sub 0 times e to the kt. There is initially 800 grams of the substance. So if I put in 800 for that initial value, the formula looks like a of t equals 800 times e to the kt. Notice that if we plug 0 in for t, no matter what k is, k times 0 is 0, e to the 0 is 1, 800 times 1 is 800, and we get 800 out of the formula. After 5 years, there is 400 grams. So that's telling us that if we plug 5 in for t, what comes out for the amount should be 400. So a of 5, that is 800 times e to the k times 5, should equal 400. Then taking that equation and solving it for k means first we divide both sides by 800. So e to the 5k equals 400 divided by 800, which is 1/2. Then how do we get rid of the e? With ln. Take the natural logarithm of both sides and we get 5k equals the natural log of 1/2. And then how do we go from 5k to just k? Divide both sides by 5. So k equals the ln of 1/2 divided by 5, which is approximately negative 0.138629. So now our formula for the amount after t number of years is 800 times e to that number, which is negative 0.138629 t. Now for the question, at what time will there be 100 grams? What is t so that the amount after t number of years is equal to 100? So set the formula for a of t equal to 100 and then solve for t. To do that, we divide both sides by 800, take natural logs of both sides, and then divide both sides by that number in front of the t, and we end up with t equals 15. So that's the answer. After 15 years, there will be 100 grams. Now, there's a sort of a shortcut way of figuring that out. There was initially 800 grams of the substance, and after 5 years, it had gotten down to half that amount, 400, which was half of the 800 that we started with. So that means that 5 years, that amount of time, was the amount of time for half of the amount to decay or disappear. We call that amount of time the half-life. So if it took 5 years to get from 800 down to 400, that means that 5 years was the half-life of this substance. So the half-life is 5 years, which means that with each 5 years that go by, half of the substance decays or disappears. We have half of it remaining. So after 0 years, to start with, we had 800 grams. After one half-life, 5 years had gone by, we were down to 400 grams. After another 5 years go by, 10 years in all, we're down to half of 400, which is 200. So after another 5 years go by, after 15 years in all, we're down to half of 200, which is 100 grams. So that's the answer to our question. After 15 years, 3 half-lives, it's gone from 800 to 400 to 200 to 100. If we let another 5 years go by, it'll be down to half of that, 50 grams, and so on. So there was initially 800 grams of the substance. After 5 years, there was 400 grams. And we used that information to work out the value of K, which was the ln of 1/2 divided by, in this example, 5, in general, the half-life. So for this kind of situation, the number we use for K is the natural log of 1/2 divided by the half-life. If you know what the half-life is, then right away you can say what number goes here for k. It's the natural log of 1/2 divided by the half-life. So in general, when you have a situation involving exponential decay, the formula for how much of the substance remains after t amount of time follows this kind of a formula, this kind of a pattern. The a sub 0 is the initial amount. It's the amount when time t equals 0. And the k, the growth constant, the number that t is being multiplied by up in the e to the kt, that number is the natural log of 1/2 divided by the half-life. So if a of t equals 10 times e to the negative 3t, that's an example of that kind of a formula. The 10 would be the initial amount, and the negative 3 would be the k. So negative 3 would equal natural log of 1/2 divided by the half-life. Sorry, I had to go back and fix this. This was supposed to be the negative 3 for the k. So k, the negative 3, equals the ln of 1/2 divided by the half-life. And then to solve that equation, you can multiply both sides by the half-life, divide both sides by negative 3. And it turns out that the half-life is ln of 1/2 divided by negative 3, which comes out on the calculator as about 0.231049. So that would be in whatever units t is in, years or whatever. That's the half-life. That's how long it would take in years or whatever units t is in before the amount that you have left reaches half of the amount you start with. In this example, the starting amount is 10. So after this much time, the amount you had left would be 5. And then after this much more time, it would be down to 2.5. And after this many more years, it would be down to half of that, and so on. So I'm going to be coming back for one more video to work through an actual sort of real world kind of application of this involving carbon dating. See you then.